Georgia. And Allison is a PhD student in the Behavioral and Brain Sciences program of the Psychology department. So that means we are moving slightly discipline-wise, which is great because when we talk about space and time, it's certainly not a single discipline that knows everything, has all the wisdom, and cross-disciplinary boundaries here. Over to you.
Okay. So I'm going to be talking to you today about capuchin monkeys and modeling their behavior using GIS techniques. Just to give you an introduction about capuchin monkeys, these are generalized quadrupedal primates that live in South America. They are highly manipulative, so that means that they are able to use tools in their environment, which is a unique behavior for this animal. In fact, for many primates, it's a very intelligent behavior on their part. They use hammerstones, anvils, and they use those two elements to crack open palm nuts to get the very nutritious meat out of the inside of those nuts. We have some questions about their behavior that we can answer in a spatial way. One of those questions is, what are their microhabitat preferences? Within their home range, what types of environmental characteristics do they prefer to move through? And that question has implications for their behavior and understanding their intelligence. First of all, we're interested in their tool use behavior, and so these environmental characteristics might tell us a little bit about what types of landscapes are best suited for facilitating tool use in non-human animals. In addition, we're interested in how these animals navigate. And so what elements they are preferring to move through is an important question in understanding how well they manage to use those types of habitats as they move through their environment. So I'm going to show you a quick video because just to give you an idea of what that tool use behavior is and how it looks. So you can see this particular individual is taking several tries to crack open one particular palm nut, and that's because these nuts are very, very tough. I make a comparison in the States that they're many times harder than walnuts, but they're particular. You see them switching hammerstones there. They're particular with respect to the weight of the hammerstones that they use to crack open different types of nuts, and they prefer ones that are heavier for more difficult to open nuts. And as I said before, this is a highly intelligent behavior that's specific to this type of primate. You do see similar behavior in chimpanzees, but not in any other species of primate. So as I said before, the question that we're interested in answering spatially is, what habitat characteristics are preferred by these monkeys as they move through their home range? So we wanted to create a raster layer of the probability of any particular pixel in the landscape being used by the capuchin monkeys in their daily movements, and that would be in terms of probability of use. So the first step that we executed to complete this goal was parsing out environmental components of their home range using spectral mixing analysis. And then we used maximum entropy to predict habitat use based on those environmental components from the spectral mixing analysis, and also from point observations that we had taken in the field, seeing where they were moving. Our study site is in the northeast section of Brazil, in Piauí State. And this landscape is seasonally dry. It is considered somewhere in the boundary between Cerrado and Caatinga. And the landscape itself is punctuated by steep ridges and plateaus. So we have these, you can see see here the steep ridges that we're talking about. These are significant barriers to the monkeys moving through their home range. But they also may present significant landmarks for their movement as well. You see the vegetation in this area transitions from sparse trees and shrubs to low grasses. And just to give you an idea where we're located. So collecting data, we followed the Capuchin group from dawn to dusk for approximately 10 days per month between October 2008 and September 2009. The data collection is ongoing, or the group is being observed continually, but this was the data for this particular analysis. Points are collected at 5-minute intervals, so every 5 minutes we get a position of approximately the center of the monkey group. And there might be anywhere between 12 and 18 individuals in the group, so we visually estimate the center of that group. And if the center of the group is greater than 20 meters from the observer, we would project the point to the approximate position of the center of the monkey group. This happened frequently when the monkeys were actually up on the sides of cliffs, so you can't actually be there beside them, and so it's easier to project. And here's an example of that. So I know he's kind of hard to see. He's about the same color as the background, but there he is. So our raw data consisted of nearly 7,000 observation points. We deleted all of the incomplete daily follows where we might lose the Capuchin group at some point during the day. And we corrected all of the observations that were approximate using right-angle trigonometry. We removed any points that were less than 30 meters apart, and that gave us a remainder of about 862 observation points for the model building. So I mentioned this spectral mixing analysis a moment ago. This was done using a Landsat image that was geometrically and atmospherically corrected, and we produced fraction images representing n numbers in the environment. So that process consisted of generating a minimum noise fraction image to reduce image dimensionality. And that was used as an input for an n-dimension visualizer in ND. So that gave us these 3 n numbers: vegetation, green vegetation, bare soil, and what we call dark M member, which might represent some measure of moisture in the soil or water standing, although there's not a lot of that in the environment where we're observing the monkeys. We went to the field in May of 2010 and qualitatively verified the results of these spectral mixing analysis. So we located sites within the home range and estimated fractional coverage visually. So you can see that there is some influence of human patterns in the home range of the monkeys. You see them here in the center, moving down a small road. There are areas of very dense vegetation, as you see here on the right, and then areas of complete bare soil, so we get a pretty good range. So we use those environmental inputs to create a maximum entropy model of the probability of use of any point in the home range of the monkeys. To do that, we use MaxInt software. It's frequently used to model species distributions over much larger geographic areas. The purpose of this type of modeling is to investigate the interaction between species distributions and environmental features. And with MaxInt modeling, we can have continuous or categorical variables, and the output, you get a variety of options, but we're using logistic output, which the output is the probability between 0 and 1 of the use of any particular pixel in the home range. So, as I said before, we wish to define a model of the Capuchin home range using those fractional coverage variables. We wanted to see how well that works. We tried the 3 and members that I mentioned to you before, but also based on our observations in the field, we felt that these significant topographic variables or changes in elevation presented a important environmental constraint on their movement. So we incorporated the digital elevation model, ASTRD, in the MaxEnt model. So I'm just going to run really quickly. These are just from the presence points. The presence points for elevation here, and you see them clustered right in the 400 meter elevation range, right around 0.3 shade. It's a bit of bigger range for soil, between 0.2 and 0.4 soil. And in the approximate 50% green vegetation. So those are the distributions of our presence points for the monkeys. So in creating the MaxEnt model, we had those 862 presence points that I mentioned before. We set aside 20% of those for a random test, and generated 10,000 background points over our area of interest. Those background points function to inform the model of the environmental variability in our environmental variables. So across the home range, how much does green vegetation, soil, shade, and elevation vary within their home range? And those are our inputs. We tested a variety of models, one including all 4 of those variables: elevation, vegetation, soil, and shade, and then with fewer combinations of those variables. Our best model was the one including all of our variables, and that had the highest AUC value. I'm going to show you that in just a moment. So here's the output straight out of MaxEnt. We have a range of probability across the home range from 95% probability to nearly 0% probability of presence. A couple of model evaluators that come from the MaxEnt model. We see emission versus predicted area. This is with increasing thresholds. If you said the cutoff point for absence versus presence of the monkeys, increasing thresholds as you go along the x-axis on that top graph. We see approximate 1-to-1 ratio between the predicted values of occurrence probability and the probabilities of occurrence selected at these threshold values. If we take a look at our AUC fit, or the ROC fit, this is a random model. We would expect if the model performed no better than random, we'd have a 50% model, and that's that black line you see through the middle. And our test AUC, area under the curve value, was 0.775. So this shows you our probability of presence at varying values of each of the variables. And you see, I'm going to show you these all together. Elevation is similar for both elevation as an entire model and elevation alone. We take a look at vegetation, soil, and shade, though they change a lot depending on whether they're incorporated into the entire model or whether they're used alone. And we probably are seeing some interaction between those 3 variables, vegetation, soil, and shade. So this is the MaxEnt output, with red showing higher levels of probability of presence, and we can see the clustering of our monkey group in those areas. Those areas also tend to follow low elevation and green vegetation. So we see some area of water and also area of low elevation. And this is that same model, just draped over the digital elevation model. So we see we see the mohos, or the ridges, in the environment, and we see how the monkey groups in the green dots, which is a little hard to see, but they're moving mainly in the flatter areas in and around these ridges. But one other significant thing is that they seem to be staying very close to the ridges. And that is likely because that's where they find those hammerstones and often the ambles that come off of the ridges, off the sides of the ridges, and that's what they use to crack open those walnuts. So that's likely an important variable, is the proximity to the ridges. These graphs show a jackknife, so the way this works is testing each of the variables either alone or without that variable. In the dark blue you see with only that variable, and then the lighter blue you see without the variable, and then the top is elevation, shade, soil, and vegetation, and then the entire model, as we see here. So gain, the first two are measures of model fit. A higher gain is an indicator of how well your presence points are fitting the model in comparison to all the background points. And we see that each of these variables taken on their own are not very good at contributing to gain, but taken together they work well. And then at the bottom, that's area under the curve, so it's another measure of our model fit. What we see is that green vegetation is contributing the greatest amount to our model fit, with soil, and then elevation, and then shade following. We do see some spatial structure in the model with a range of about 1,500 meters, which is much closer together than what we would expect our monkey points to be limited to. So while we see that this model is spatially autocorrelated, we do think that this doesn't have a whole lot of impact on the functionality of the model, for the simple fact that we are attempting to measure or model a spatially autocorrelated phenomenon, which is animal home ranges. So the points that we're observing are naturally going to be correlated with space and time. So what we've shown is that spectral mixing analysis can quantify relevant environmental variables for the movement of these monkeys. Most notably, green vegetation. That was very important for defining the microhabitat variables that are important for their movement. Capuchin monkeys in this field site tend to prefer areas of moderate to low elevation. And MaxNet can be used to create a model of animal home range use. However, we believe that these results should be specifically applied to the purpose compatible with the source of our data. Our data was directly coming from observations from following the monkeys and from this particular group of monkeys. We don't think that this could be extrapolated directly to another group of monkeys or to another area of the world. And in fact, that's not the purpose of our work. Right now, what we're working on doing is to be able to model their movement within their home range. And so this probability model gives us an estimate of how likely they are to be anywhere in their home range. So expanding it beyond their home range is not really of our interest right now. As I mentioned before, their proximity to ridges is probably a very important environmental variable for predicting where these monkeys will be located. So future models need to incorporate that variable in order to account for their preference for being close to the ridges. So how can we apply this model? We think that the probability of capuchin monkey habitat use within the home range can be used to predict their use in changing environmental conditions, which, as we all know, is an important conservation effort. And we are most interested in applying this MaxNet model to creating a model of movement. What I haven't shown you here is the use of these probabilities to create a surface across which the monkeys will move, and that is something else that we're working on. So the probability value of the surface of that is a friction surface against which the monkeys would be moving, and we can create paths to predict where and how they move through their environment based on this maximum entropy model of their probability of being in any location in their home range. So really quickly, I'd just like to thank the Center for Remote Sensing and Mapping at UGA and all these folks you see here. And thank you very much.
Thank you. And just let me start with the first question. You have collected point data over space and time, and in your analysis you were only looking after space. Wouldn't it be interesting for you as well to look after time? For example, at which time of the day are the monkeys where?
I think that's probably a really interesting question. One significant thing that we think could be affecting their movement choices would be sun position or the heat of the day. So you have these huge ridges that may be contributing not only as landmarks, not only as barriers for movement, but also as significant contributors for shade for their protection from the sun. So I think that's probably that would be an interesting thing to take a look at.
More questions? Yes.
So just had two questions for you. First one was, do you think the fact that you're following them might have had a bit of an influence on their movements through the area?
I'll forget them all. So let me answer that one, and then we'll go to the next one. So in fact, these monkeys are habituated to human presence. So they've been followed for the past 7 years, if I can count correctly, thinking on the spot, 7 or 8 years. So they're accustomed to humans being around them, and even prior to that, they were being observed by this kind of ecotourism business that the landowners had set up. So I can get as close as to me, to him, to them, and they don't seem to be too bothered by it. Okay.
And another question was, when you were developing accent models, did you look at sort of various some of the model inputs as well, to do things like the regularization inputs, and did you use any sort of model selection techniques to select your optimal model?
Yeah, I did. In fact, I kind of glossed over that for a moment there, didn't I? So gain is regularized, and that's in the far right-hand column there. What we saw was that with differing models, depending on which variables we included, the best model was the one including elevation, vegetation, soil, and shade. Maxent has some built-in mechanisms for avoiding the effect of including more and more variables in your model and that causing a better fit. So we didn't think that was, in fact, 4 variables is a very small number of variables for a Maxent model. So we thought that was the best fit on a number of these variables.
Let's actually add as well, did you look at sort of other model selection techniques apart from area under the curve?
Yeah, in fact, so test gain, you see there on the far right, that is a model, a kind of measure of model fit as well. So that is a measure of how likely it is that your presence points are predicted, as opposed to any of the background points.
Right, here I saw another question over there. I think that's the last question. So.
Yeah, you used Landsat. Isn't the resolution of Landsat limiting? Wouldn't you be able to tell more about the habitat from QuickWork, for example?
Yeah, that's a really good point. In fact, so we got 30-meter pixels, and we're talking about a very small area relative. I mean, their home ranges are relatively small. So one thing we've been working with, and we presented at ISPRS this year, American Society, and we presented Worldview 2 using a similar technique. One thing that we see is that, in fact, it becomes difficult. You get individual trees as opposed to an area of microhabitat that's extreme micro, and so it's hard to generalize how they would move even from one tree to another. And the point of this, in fact, is we're hoping to model movement. So we don't want to suggest with our model that it would be impossible for them to move from one tree to another. So it's something that we're interested in and something we're taking a look at.
All right, I'm aware that there are several other questions in the room. I suggest that these people contact Allison in coffee break to allow all the other people coffee break. Thank you, Allison. And thanks again to all speakers.